Hello, so for my ITP 348 final project, I designed an intercooler sprayer. In this video, I'll explain how and why I did it. I designed this intercooler sprayer to work with turbocharged cars. A turbo is basically a device that utilizes the kinetic energy of exhaust gases to compress and force air inside the engine. Turbos are often used in high-performance applications to increase the power output of an engine. The problem is that when air is compressed, its temperature increases, and hot air going inside the engine can put it in a knock-prone condition. Knock is when the air-fuel mixture inside the engine compresses and combusts in an uncontrollable manner. This usually leads to engine failure. For this reason, turbo cars usually come with an intercooler, which is a heat exchanger used to cool down the compressed air sent from the turbo and into the engine. The problem with intercoolers is that in high-performance applications, they can become heat-soaked and fail to effectively cool down the compressed air. To remedy this issue, I designed a device to spray water in front of the intercooler to increase its convective heat transfer capacity. So my device consists of 2 op amps, one TMP36 temperature sensor, a button to test my circuits relay, an OLED screen, a relay, a power supply, 2 thermocouples, and a water pump. The purpose of the thermocouples are to read in temperature data upstream and downstream of the intercooler. This data and calculations from these numbers are published to the cloud. In a motorsport application, this live data can be useful for trackside engineers. The problem with thermocouples is that the voltage that they output is very small, so I use an op amp to amplify the voltages for the particle to read. In the next picture, I'll explain how I wired my op amp. By wiring an op amp in the way shown in the circuit diagram, I was able to amplify the voltage output of the thermocouple by 500. This number is called the gain and is achieved by using a resistor of 5010 ohms. One thing to note is that the op amp requires a power supply to amplify voltage. For this reason, I used an additional power supply to get a negative voltage of 3.3 volts. The other 3.3 volts was provided by the argon. I also wired in a TMP36 temperature sensor to be used in conjunction with the thermocouples to help calibrate their voltage offset. To power the pump, I tapped into a fuse inside my car. This is because the argon's output is limited to 3.3 volts and 500 milliamps. The output from the fuse I tapped into read 12 volts and 10 amps. To turn the pump on and off, I used the relay shown in the next picture. With the pump and relay wired in this way, I was able to send a higher low signal from digital pin 2 to turn the pump on and off despite it utilizing a completely different power supply. The last main component of my device is an OLED screen. I use this to display the different settings the device is operating on. These modes are toggled by an IFTT button, which calls a function I wrote. Mode 1 of my device turns on the pump to spray water on the intercooler if the temperature delta between the upstream and downstream intercooler decreases below 20 degrees Fahrenheit. Unfortunately, I was unable to get a recording of this in action because reaching this temperature delta required the car to be moving. Mode 2 turns on the pump for 15 seconds every 15 seconds. This setting is useful in traffic situations or in the staging phase of a race. The third and last mode turns the pump on to run endlessly. This setting is useful in a race that might only consist of one lap. Given all this, to operate the device, a user would simply need to fill the reservoir of the water pump with distilled water. The only settings or inputs the user would need to interface with is a toggle button designed to switch through the 3 different modes.